gauge for WebAssign. So hopefully all of that should be okay. And the computer's not on. Okay, so we will let the computer get on. So that should be the only differences is we're still at 10% extra credit if you do it ahead of time. I do have implemented 2 new policies in my syllabi based on some things that happened last semester, but it wasn't really a problem in you guys' class, so I don't expect it to be a problem going forward. One is a new cell phone policy, and that cell phone policy is if it's an inappropriate use of the cell phone, I do a 3 strikes and you're out. Because I use the cell phone in class, so I can't totally eliminate the cell phone. But what I don't want is the distractive behavior of somebody texting their buddies all the time. In a couple of my classes last semester, I literally was talking to the backs of cell phones. And I don't mind people taking pictures of the screen. I use it as the polling device. I use your cell phone as a tool. And so I can't totally eliminate it, but I can eliminate the distractive behavior. And so the first one, you get a warning. Second one, I'll ask you to leave, and you're not counted as being in class. And the third time, I'll just drop you from the class. Because if you're in there texting your buddies, you're certainly not learning anything in class. That's kind of why that's the case there. Also, I've kind of implemented a more of an attendance policy. I am taking roll all the way around, so there will be a sign-up sheet going forward on both sides, just to be able to keep track, because I can't. But when it's 6 and 11, it's a little easier. One of my classes, I have 38 combined, and there's no way I'm going to keep up attendance in 38. But when I have smaller classes, it's a little more difficult. So let's see if I can get stuff up here. Office hours. For you guys over in Enid, I am on Enid campus all day on Fridays. I'll get there about 7:30 in the morning, and I am there until after 2:30 in the afternoon. I have a class at 10:30 that I do ITV, and then I have a class at 1:30 that I do ITV. So from 11:30 to 1:30, I'm in my office. And so you guys will have definitely more access if you need help. And Physics 2, you kind of need more help than Physics 1, right? It's just the nature of the beast. But there's some good parts of the nature of the beast on that too, and we'll talk about that here in just a sec. Because Physics 2 is the way it is, I do some things different. What we're going to start out with today is we will start with simple harmonic motion and wave motion. So we're going to do simple harmonic motion first. We do wave motion. Did you guys over in Enid, did you have lab yesterday, or is your lab today?
He canceled it yesterday.
Okay, yeah, I know why. but you guys typically will have it on Tuesday? Yeah. Okay, that helps me out. Now, did you guys, and I want this for both sides, did you guys got a lab manual over here? Okay. The Physics 2 lab manual I'm not happy with, and I know Christian probably didn't have the Physics 2 lab manual until yesterday. So that's one of the reasons that lab was there. You guys will still have lab today because you guys have lab on Wednesdays. So you guys will still have lab. So that will keep me sequenced. I think we're going to be totally fine sequence-wise. But we're going to do simple harmonic motion to start. Then we do sound. Then we do static electricity, starting with electricity and magnetism. So if you start to think about that, we do simple harmonic motion, which is still kind of mechanics, but then we get into sound. Okay, that's a little weird. And then we go into electricity. Well, that's a little weird. Then we have circuits. Well, that gets us a little strange stuff too. And we got magnetism, and magnetism's really unusual and weird. Then we get into optics. Well, it turns out that it's not like mechanics where everything builds on itself. We do it this way because of how we explain things and how we bring things together. So, good news number one, there is no comprehensive final in this class. Good news number one, no comprehensive final. Bad news is you're probably going to have 5 exams, all right? The final will be over optics only, all right? So the final is over optics only. And then I try to break up the exams to where when we switch topics, okay? So there'll be an exam, and you'll get an exam fairly early because we'll get through simple harmonic motion and sound probably by the end of next week. So we'll have an exam in week 3 just because I'm going to cover simple harmonic motion and sound, and those two are very related. It doesn't seem that way, but they are. Those two are very related. And then we'll go into electricity. You'll get a test over electricity principles, and then we'll get a test over circuits, and then we'll get a test over magnetism. So you're going to get a variety. It'll be 5 tests. Typically, that's how it works out. One of the tests I've done it as a take-home test the entire part. I have done it as a partial in-class take-home test. We'll just see how we are on time at this point, when we get to that point. The reason I do it is when we get to circuits, the problems aren't hard, they're just tedious and long. Because you're figuring out voltages over different resistors, you're figuring out where the current is going in the circuit. They're not hard problems, they're just long because you're solving for multiple variables. And because of that, trying to do a test in an hour and 15 minutes is just next to impossible. Because if you go down, now if you go down the right path the first time, and then you're going, oh, I shouldn't have done, that's the hard way to do it. So, because some of them, they're quick and easy, and if you see it the first time, great. If you don't, you gotta kind of work through it. So that test, I always have a partial take home on that test, whether I do part in class or not. So that one is kind of, it's a little different than how I do Physics 1. We'll still be doing multiple choice with the option for partial credit. So that part is going to be the same. Other than that, quizzes will be the same. They'll be on there. Homework is still through WebAssign. It's kind of the same. There's going to be now there will be an assessment quiz, just like I've done before. That will be comprehensive at the end of the semester, but it's take home, and it's open well before the end of the semester. So that should help you out on that. Okay, questions about overall policies, practices. All right, I will talk about the last lab. The last lab is not hard, but it has some challenges associated with it. And I'm loath to give it up. I really like the last lab. It's a pinhole camera. And there are multiple ways to do pinhole cameras. If you ever go out and Google, you can find how to make, I think there's 255 different methodologies to make pinhole cameras. They're very simple to make, they're easy to make. So that part of the lab is not your challenge. Your challenge is how you're going to provide the images. And no matter which choice you use, it's going to take a little bit of effort and working through it. There are 3 methods, or it's actually 4 methods of actually getting an image. One is the traditional film method, and when I first started teaching back, you could still get film developed at Walgreens pretty easy. You can still get film developed at Walmart now, but you could usually go in and get your 1-hour photo done, and it was great. You could go in and see if you got it done. Now, I think you have to plan for a week to get film developed. So that's problem number 1. If you use the film route, although the film route does do for some really cool pictures. I mean, it's a really cool way to do it. So the film route is a little difficult. There is the photosensitive paper route. All right. First of all, photosensitive paper tends to be expensive, but if you've got somebody who's got access to photosensitive paper, that's a way to do it. But I will tell you the exposure times do require bright sunlight in order to do it. And you're talking something on the order of 12 to 16 hours of exposure time in order to use the photosensitive paper in order to get an image. So that route is just a little time intensive. There's the route that if you have a digital camera, you actually have a digital camera and you can use a lens cover to create your image. That works really well, and I've had some folks really get some really cool images with that. You can also take an old webcam and take it apart and make your own. I've done that one too. That one's actually pretty cool too. But it takes you a little while to finagle and finesse how you're going to get those spacings out correctly and how it's going to get onto your CCD array in order to get your image. So that one takes a little bit of finagling, and so it takes you some time to figure that part out. So that is a time kind of sink for there. But the people who have done it have had great images. They're really, really cool. The final way is instead of making a pinhole camera, you end up making a pinhole projector, and you actually capture the image much like you're capturing the image on a screen. And it takes some geometry finagling with your pinhole camera in order to do it. So the camera itself is not hard. The overall project is not hard. There is some time-consuming aspect. So I'm warning you right now, today, that don't wait till the last minute. I also try to warn you ahead of time because spring break is a good time to play with this. Because I've had some folks do it that they've gone on a ski trip and the really bright light at the ski trip, you know, and when you're up reflecting off the snow, they've gotten some really cool images that way. Just because you get extra rays, extra brightness, and that works. So spring break is a good time to do the pinhole camera. And we typically require 3 images. Now, I say 3 images, it doesn't necessarily have to have it come out and work out and you have these wonderful, because if you go and look at pinhole camera images, you'll see some really cool ones and really ornate. I think we all will take that we can figure out what it is that you're taking a picture of. Okay? We can figure it out. And that even takes, we can figure it out with a little bit of imagination, okay? So it's obvious that you've taken a picture of something and it's not that you just exposed the film. That's really, and usually usually almost everybody will get 1 really, really good image and 2 that are like, okay, if you hold your head and hold your tongue just right, you can tell this is a lamp. So we're not after, you know, the museum quality type images, but I do want to give you a heads up on that one because it does take a little bit of time. I think Mr. Grimm requires you on this side, and I'm sure Dr. Samamanu is probably going to follow that lead, that you have to show him your camera. You know, he kind of approves your camera and your camera design, and then you turn in the written report at the end. So that's the last, and I'm loath to give that one up because it is so, the optics and the physics is so simple and it's elegant and it's really nice to see that simple stuff. So any questions on that? Okay, so I just wanted to call up Blackboard to see what I actually have in Blackboard right now, because I set up Blackboard before break and I haven't had a chance to go back and go, what did I actually set up and everything else? So let me go there real quick. And then we'll get started. Oh yeah, you're gonna do it a bunch. Okay, all right. Okay, I've got in here for us is there's the course key to link up to WebAssign. My hours are generally correct, although I've made a little bit of a shift for you guys in Tonkawa. I had a 2:30 class on Monday. That class is actually meeting at 9 o'clock on Tuesdays. Not a big shift, so that means I'm in my office Monday afternoons more than what I was expecting to be. And on Tuesdays, I may not be in my office at 9 o'clock. And then, like I said, in Enid, I'm there quite a bit. So you guys will have me out there. Okay. And then the grading scale is the same. There's the course key. I will post lots of stuff in the course materials and assignments. I just haven't dived in for that yet here. Then where else was it? I haven't even hooked up WebAssign, so we will do that right now. Oh, good. Physics is an experimental topic, and as such, you guys are participating in an experiment. I don't know, when you guys log into WebAssign, and particularly if you're in a different text or have WebAssign for your math class or have WebAssign for or have a Cengage book for a variety of other things, and it's going to look different than last semester. WebAssign is in the process of doing a beta test for a new student user interface. So my WebAssign, which always looked a little different than yours anyway, my WebAssign is going to look the same. Your WebAssign is going to look different. And they're going to be asking you to fill out a couple surveys, and usually, and if they call you and do a one-on-one focus type thing, they usually offer like Amazon gift cards, that kind of stuff to participate. It's supposed to make the user interface a lot more intuitive, supposed to make it easier, supposed to make it do a variety of things. So your user interface when you go into WebAssign is going to look a little bit different than what you had expected before. And that's going to be rolling out, and it may change from week to week because they're rolling out a beta test associated with it. So if you're having problems with it, holler. But it's supposed to make, because one of the complaints everybody's been having about WebAssign is that WebAssign is old and clunky, and if you're in something like Connect, it's a little easier to move around in Connect. If you're in something else, it's like MindTap or a few other things, it's a little easier to move around. So they're really trying to work on that student user interface. And so and all my physics classes are part of the pilot. So that and which is really nice because you guys are good for them because you used WebAssign in physics last semester, and you'll use it this semester, and you'll be in the new user interface, and you'll be in the new user interface, so you'll be able to see the differences, and they'll ask you what you like better, what you don't like, what didn't work. And if it's like, I'm too frustrated with this, and you can opt out and go to the old one. Okay, so you can, and then they'll call you and ask you why you did that, But again, Cengage, we've had, every time I've done a pilot with Cengage, you guys as students have benefited greatly. One time I did a pilot and they provided the textbook totally free. So you guys, and like I said, gift cards, interviews, they give you, so you may get emails from them saying, hey, how's this working? And get an opportunity for a variety of different things. So that's why I went ahead and volunteered, because you guys usually end up with a benefit. So you've got the getting started, and that's due by Friday. We've got the sound pre-work, and that's due by Friday. And then we've got the simple harmonic motion, which we're going to get there. Other things that I do different in Physics 2 than I do in Physics 1 is, one thing that I will probably post pretty quickly is I ask you to find examples and videotape examples of certain things. One example I want you to look for is an example of simple harmonic motion out there, and unfortunately that can't be a clock pendulum, because a clock pendulum is pretty standard representation for simple harmonic motion. A spring going up and down is pretty standard. So those two are like ixnay. And one of the examples that I will post. So by next Wednesday, you're gonna have to, get a 30-second or a 10-second clip of something that is simple harmonic motion, and you can take that with your phone, little video with your phone, or you can capture it off the computer somewhere. So I do a little bit more of that so we can actually see some more real life type applications. The second one that I always do is I need a sound recording of the Doppler effect. And please no sirens. I really am tired of sirens. I'm tired of police car sirens. And there are lots of things that have a Doppler effect out there that aren't police car sirens or train sirens, okay? So I give high points for creativity on that one. Because you can actually do the Doppler effect down the hallway of the dorm. So be creative, okay? Be creative. And that one I'll post next week for you guys to be able to put stuff in there. I also do pictures of static electricity, so you can start thinking about those. Again, I'm trying to do more real life, where does this stuff come in? And so that we've got a few more fun assignments like that instead of just working problems all the time. All right. Okay, we good? You guys good over there in Enid? Which room are you in? You in Zoller 110? Can't hear you.
Yeah.
Okay, how's the mechanical sound in there? It doesn't seem like it's too bad today.
It's actually good for 110.
That's what I'm thinking. That's what I'm thinking. Okay. All right. So you ready to dive in? Okay. All right. Physics is an experimental sport, right? Okay. That's not bad. You guys see how that works on the screen? It's not bad. I have a new toy. And it's going to save me a ton of paper, and it's going to save me a ton of markers. It's liquid paper, okay? It's liquid paper. I love it. It's totally cool, man. It's totally cool. So we all remember Hooke's Law. Might be able, let's see how this works if I turn the light off, because we played with it in this room. Each room is slightly different. No, I gotta have the light on. Each room is slightly different as to how well this comes through with a glare or not. So we all remember Hooke's Law. That was our force was equal to minus kx. And that was designed by the fact that if I have my apparatus hanging up here, and I've got my spring, and we would look at this, we were always looking at my change in x down here, and that stretch was based on whatever force we were applying. Okay, we did that, we got our force applied, we could calculate, so if I had something that was 0.5 kilograms, and we put that on there, and we did our stretch, and we say, let's say it's stretched. We're going to go ahead and say it's stretched 0.15 meters. I could calculate my spring constant and with the negative, and we're just going to do the magnitude here. We want the magnitude of the spring constant. So it would be mg is equal to kx, because again, I'm doing the magnitude. And I would get mg divided by x is going to give me my k, and if I plug in my numbers, I get 0.5 times my 1 point, oops, come over here. I get my 0.5 times my 0.15 divided by, oops, boy, I can't do anything today. Here's the other fun part. I can erase on my liquid paper without changing anything around. So we will do that now. So I'm going to get my 0.5 times my 9.8 divided by my 0.15. And this will give me newtons on top, meters on the bottom, and somebody got the calculator handy? Because I didn't bring mine in. .6 Newton meters, and that's my spring constant. So when you guys go into lab and you're doing your simple harmonic motion lab, guess what's the first thing you got to do? Figure out the spring constant for your spring. Okay? Figure out the spring constant for the spring. But now, we've done this, right? We've done Hooke's law. We know that we get a nice linear function. Everything works out really cool. But we also know something else happens when we have a spring that looks like this. If I do this and I push it down and I let go, what's it going to do? It's going to bounce up and down, right? We know that it does this little bouncy up and down thing. Okay? So what we end up seeing is we get, if I were to put a pin on here, and I were to do a piece of paper, and I'm doing a piece of paper, and I let that pin mark on that paper, and I'm pulling this paper with respect to time, I'm going to get something that looks like this. Right? We get a wave that looks like that. And if we think back to math class, somewhere in math class, what do they tell us that looks like? What?
It's like waves.
It's a wave, but what kind of wave is it?
Sound wave?
No, it's not a sound wave. We're talking mathematics. So if I'm in math class, they're not going to tell me it's any kind of real wave, which is one of the things that causes us a problem with math and science, because science is, or math is the language of science. So one of the real problems is we don't tell you what that is. But if I were to go to my book or I go to my graphing calculator, that would either be a sine wave or a cosine wave. And we typically refer to it as a sine wave. Right? We typically refer to it as a sine wave, partially because of this. If I take sine of an angle, any angle, and I can't remember if it's plus or minus, but 90 degrees, that equals the cosine of that angle. So they're just off by a 90-degree phase. And basically what that means by being off of a 90-degree phase, punch in the cosine of 1, or yeah, punch in the cosine of 1.
Like cosine 1.
Cosine 1.
This is 0.99.
Okay, 0.99 cosine of, are you in radians? Punch it in radians.
Yeah, what's the radians?
Okay,
Cosine 0.54.
okay. Punch in the cosine of 0 then.
1.
Yeah, okay. All right. So if I do the cosine of 0 degrees, that equals 1, right? That's what we said? Okay. Sine of 0 degrees is equal to 0. And basically what happens is if I draw from on a mathematics point of view, this is my cosine wave. And if I draw from a sine point of view, this is my sine wave. So they have the same shape, right? They got the same shape. They've got the same behavior. The difference is if this is t is equal to 0, where I start. Where I'm starting, if t is equal to 0 on the cosine, is at 1. where I'm starting at t is equal to 0 on the sign, it's 0. There's no real difference between the two other than where I start. And that's why we call it a phase angle. Okay, that's exactly why we call it a phase angle. So that's where it comes in. So in your book and in your lab, you may see two different things. Okay, you may see two different things. So if I go back here, so if I'm looking at my spring, and we know it's bouncing up and down, and I can call this a y direction. Remember, y is just a variable, okay, and I'm going up and down. The description of this motion, any position y, can be described as a, which is just a number, cosine 2 pi times the frequency times time. So where I'm at is any time I'm looking at where this is, I can describe the motion going up and down with respect to time based on these factors. So let's look at what those factors are. So I have a midpoint for my motion, all right? This is my midpoint for my motion. And this is the highest it goes, and this is the lowest it goes. That's the highest it goes, and this is the lowest it goes. And this is the amplitude. And the amplitude is just from this point here. And when I look at that on this scale, this is my A. It is not peak to peak, okay? It is not valley to valley. It's that space or this displacement from that 0. That's called the amplitude, and that is what that A is. That's what that A is. So we know it's bouncing up and down, right? We know it's bouncing up and down. Now that bouncing up and down, and that's why I say we always talk about the pendulum being simple harmonic motion, because my pendulum also goes from here to here. Okay, it's swinging back and forth on my pendulum, and we also know that that is the amplitude for the pendulum. So if I put a pin on my pendulum and I pull a piece of paper, it's going to look the same way. I'm going to get that nice up and down sinusoidal curve. Similarly, here's the other fun part. I have a circle, and I've got a bead on a circle. And as this bead goes around, and we could say we are looking at the shadow coming in and out of the paper, as it goes around, it's going to have a position on here, and it's going to look like it's going back and forth, back and forth, back and forth, back and forth, back and forth. So we've got circular motion that can be described by the same way. So I can have a bead going around a circle, I can have a pendulum swing back and forth, I can have my mass bounce up and down on my spring. All is going to look very much the same way. But this, we know something about. We know that we have something called the period, and that's the time it takes to make one complete cycle. Okay? And we also have known that the period, because we did this in rotational motion, is 1 over the frequency. 1 over the frequency. And if you guys remember your favorite part of Physics 1, right? Everybody loved rotational motion, right? We loved it. No, I don't even like rotational motion because we don't think in circles. We don't think that way. But there's lots of things that are rotational motion, okay? There's lots of things that are rotational motion. And if we were to go back and we think about that, remember that angular frequency was 2 pi times my frequency. So the angular frequency about going around my circle was 2 pi times the frequency. So this F right here is that frequency. That F right there is my frequency. So this, all right, according to our book, okay, this is what our book is going to use. Our book is going to say that my position, and typically they use it as an X. Remember, X can be a Y or X can be whatever. They're typically going to say that my position is always going to be related to 2 pi times the frequency times time. Or I can rewrite this as X. There's my amplitude, cosine omega times time. Now, for your lab this week, it's going to say, we're going to use Y because we're going to be bouncing up and down. Make sure you guys can see it over there, Enid. We got Y. But I can write it as A sine 2 pi by frequency times time plus a phase angle. And basically what this is doing is telling us where we start. Both of these are going to give us, just like this, they're going to give us the same behavior, whether it's sine or cosine. It's just related to where I start. So depending on what physics textbook you pick up or what book you pick up, it's going to give you either the cosine or the sine. Our book gives us the cosine because it makes it a little cleaner for the next step. Sine, but it doesn't really matter. I can use the sine as well. It's going to give me the same behavior. Somewhere along the line, we talked about it, but we didn't focus a whole lot of attention on it. So if I go back to my rotational motion again, I got my angular frequency as 2 pi times my frequency, but I can relate that back to a spring system. I can relate that back to a spring system, and my spring system, if I do that, it becomes K divided by M, where K is my spring constant, and M relates to the mass that I have. So let's think about this for a second as to why we do this and why we look at spring systems. You know, we don't just go bouncing springs around, right? That's not necessarily something that we do, unless we like to do low riders. Then we get them bouncing, right? We get those low riders, and they go down and they bounce down the street. You know, unless we're doing that, and unless we want to really have fun when we're going mudding. You know, there's that part. So bouncing up and down is not necessarily something that we typically want to do. But let's think of a physical system that happens. So if I have a solid, and we know a solid's got a regular shape to it, we can think of my bonds that's in my solid as a bunch of little springs. Okay, we can think of that as a bunch of little springs. And if I put energy into this, I get those springs, and we know that the molecules are moving, right? I get motion between those molecules, and I can excite that molecule, and I can get those springs to start vibrating. And that vibration will relate to simple harmonic motion, and we can describe the motion of these vibrations in here, and I can find out a whole bunch of things about my solids. And I can know when my solid is when these bonds are going to break, and when I'm going to go from a solid to a liquid. So that's one place that we use it. The other place that we use it, how many of you microwaved your breakfast this morning? You use simple harmonic motion. Because simple harmonic motion deals with resonance frequencies. So there's my little oxygen molecule. I've got a nice covalent bond with my hydrogen. I got a nice covalent bond with my hydrogen here. And I put my energy in there to excite that lovely little bond, to create friction, to heat up my food. So we use simple harmonic motion to describe a lot of different things. And so the spring actually is a really good model for a lot of chemicals type stuff. That spring model works really, really well. The other part of simple harmonic motion is this circular motion part. So let's think of, I've got a piston in my car, right? And we know what's happening when I do the little explosion right here at the top. And I push down, I am rotating around the shaft, causing the shaft to turn the wheels. This whole behavior of this piston going up and down, simple harmonic motion. It's going to produce this lovely sine wave. All right, it's going to produce a lovely sine wave. Now we have something that works against us, and it's called dampening. And that's what we know. So if I have my lovely little spring set up here, okay, I got my lovely little spring, and it's bouncing up and down. We know what ultimately happens, right? So I've got my lovely graph here. And early on, my wave is nice, but then we notice something. It starts to do this, and we lose our amplitude, and that's called dampening. And that dampening is due to friction. Friction's not necessarily our friend. Friction can be our friend, and we get a little bit of dampening associated with friction. And so we see dampening all the time. And we can use that to our advantage, all right? We can use that to our advantage. We use it when we're dealing with our shock absorbers. We use it when we're dealing with a variety of things. We actually want to dampen that motion, and so that's one of those places. Some cases we want to use dampening, some cases we don't. The other part is a spring doesn't always look like this. When we say spring, we think of that. Well, I have a picture in here or that I've used in the past that my spring looks like this. If I have an old mechanical watch, what I've done is tighten that spring, and my watch spring is actually a circle. Okay, and that spring, that curved spring that way is actually circular. So it's not in what we traditionally think is a coil spring. The other is if you go in, how many of you drive a truck? That includes you guys over in Enid. How many of you drive a truck? All right. If I look under my truck, particularly under the bed of my truck, most trucks will have something that looks like this. I've got a piece of steel, I've got a piece of steel, I've got a piece of steel, I've got a piece of steel. It's usually 3. Some trucks will have bigger. That's called a leaf spring. Doesn't look like my coil, but it's got a leaf spring in there. Yeah, see, the tall people have trouble. I don't have that problem.
It's like the third time I've done it.
We have skirt hiders or what modesty plates in this room over here, and my tall people keep hitting them. That is not my problem. This is not my problem. It's always fun. Out in the refinery, I used to used to go out and we do investigations and stuff. I never had to duck. Most things are about 5'5", even with a hard hat on. I don't have to duck. So I mean, there are advantages. But
Finish the tomato soup though still.
I can't. I still have to have my stool. Although You guys don't know the guy over here over in Enid. You've probably, when we play Bedlam, you'll notice him. Number 44 for our basketball team is Lafayette Stone. He's a tall dude. He's tall. He came into my office, my poster had fallen down in my office, and usually I have to stand on my desk to put my poster back up. Lafayette was in my office, and I said, "Can you put that back up for me?" He didn't even have to. It just was straight across. Just straight across. So, we have issues. So, we have issues. So there's lots of different springs out there. Lots of different systems that we can deal with springs. And if you think about it, for you biology types, okay, think of the coils on grapevines. Those coils on grapevines, those are springs. Let's see, which plant is it? Well, I'm not sure if you call a Venus flytrap a plant or not. It's got a spring in it. It's got a mechanism that's a spring mechanism. So there's lots of things that we can look at from spring mechanisms that we have for simple harmonic motion. And simple harmonic motion is a nice pattern. So let's go back and let's look at our equation here. So this is our general position equation that we're going to be using. Okay. That's our and it actually describes a motion, right? It's going to tell me how high up and how low my mass is going to bounce if I have a spring system. So if I have this system right here with my mass hanging down, there's my arbitrary middle, and then it's going to bounce up and it's going to bounce down, and we'll know how far it bounces because we know what the A is. All right? Now, if I have a really long spring and a real heavy mass, the bounce is going to be slower than if I have a real light spring and maybe not so much of a heavy mass. It's going to have a nice fast bounce, right? So if I have a clock spring, we want it to bounce at 60 hertz. We want it to bounce 60 times in 1 minute. So I have a bounce. So what happens to us is this. If I give you something that looks like this, that's an equation that's describing some behavior. And if I tell you that the amplitude is in meters, that's big meters, let's do centimeters. We'll use the amplitude in centimeters here. How high is my mass going to bounce? If I give you that equation, how high is my mass going to bounce if it's in centimeters? Take a guess. If this is in centimeters, how high is it going to bounce if that's my equation?
Oh, I should have guessed. I don't want to guess and be wrong, so I did.
It's 5. No, it's not a trick question. It wasn't a trick question. It literally, you can read it right off of the equation that you're getting. It literally do that. So now if I ask you the frequency, what's going to happen is 30 is equal to 2 pi times the frequency. So the frequency is going to be 30 divided by 2 pi, and that's going to be how fast it's bouncing up and down. Which, if I ask you the period of that, that becomes 2 pi over 30 because the period is 1 over the frequency. You literally can take that equation and read, I can tell you how high it's going to go. I can tell you how fast it's going to be. Just by looking at the equation. The equation is literally describing the motion. What you're going to do in lab is you're going to bounce this, okay? You're going to bounce it up and down. You're going to find the amplitude from the graph, right? You're going to look at the graph. Your detector is going to tell you it's this. You're going to find from my graph, you're going to measure that off your graph. And you're going to get that, and we're going to have this graph, and we're going to say this goes from And basically, the other fun part is your detector's down here. And so there's going to be this bottom part, or this part right here. And that's going to be what we call Y0. That's going to be just how far away from the detector is your mass. Just how far away is it. But then my amplitude is going to be that piece there. So let's say that this becomes 3 centimeters. Then I measure the time that it takes to go from here to here. All right, because this is against time. And we find that the time that it takes to go from peak to peak, one complete cycle, is 2 seconds. So I got 3 centimeters in 2 seconds. So basically I'm going to say, okay, my Y is going to be 3 centimeters. Cosine, and then I've got 2 pi times the frequency times time, except my frequency is 1 over the period, so that's going to be 1 over 2 seconds, which is going to give me 0.5 hertz. So now I just plug in my number. I get Y is equal to 3 cosine 2 pi times 0.5 times time, which is going to give me Y is equal to 3 cosine pi t. And I have just now described the equation of motion for my bouncing spring.
When can you fix that lighting?
Oh, what happened? It did weird. Ooh, let's see what we got. Give it a second, because this doesn't respond real quick. There we go. Oh, I know what it probably did. It probably adjusted for the background. That's a little better. So 3 cosine pi times time. Okay. So, guess what? You're likely to have on a test, if I give you this, I give you x is equal to 5 cosine 30t, you're likely to have to tell me the amplitude, the frequency, the period. Amplitude, frequency, and the period just from the equation.
And the period's different than the t, right, for time?
This t, yeah, this is a capital T.
Okay.
We use a capital T for period
Little t for time?
and a little script T for time. Use capital T for period, little script T
What's
for
the thing on the 0.5 at the end, on the bottom?
0.5 hertz, Hz. Yeah, it's Hz. Okay. You guys got it? You guys good over there in Enid? Okay. All right. So, I start with X. And we've got 2 pi times my frequency times time. And you know what happens. We can't just look at position, right? Can't just do position. Can't just do position because we always want to change in position with respect to time, right? So remember that if I do velocity is a change in position with respect to time. And for those of you who are taking calculus or haven't taken calculus, this just becomes the derivative. Okay, just so you guys have a chance to see it. All right, so you have a chance to see it. But we do this change, and it turns out mathematically, if I do that change when I have a function like my cosine, this becomes negative 2 pi times the frequency times the amplitude sine 2 pi frequency times time And I can rewrite this also as minus omega A sine omega t. So I can do that. And this is the velocity at which my mass is moving. So if I have my bead going around the circle, so I got my bead going around the circle kind of gizmo here. This is the velocity, how fast, if I'm looking at it, because guess what? This looks at it in the x-plane. It's how fast is it going back and forth across that axis. That's my velocity. And we know we can't stop with just velocity, right? Can't stop with just velocity because remember that acceleration is my change in velocity with respect to time. And again, if you do get calculus, this just becomes the derivative, which we don't necessarily pay attention to for you guys. Just so you have a chance to see it, because some of you ultimately will be in calculus, and I want to link it together. And basically what we end up with then is that my acceleration is now negative 4 pi squared frequency squared amplitude cosine 2 pi times the frequency times time, or if I write it in terms of the other, I get omega squared A cosine omega t. And so I have my three equations of motion describing it. There's my first one. This is my second one. And this is my third one.
Is that the angular velocity next to t? Is that a W right?
Yeah, that's my angular velocity. It's at omega. It's at omega. See, this will focus a little better. How about that? That focused a little better. So I get my three equations. Now, if I write this out and I give you that the acceleration of my little bead going around the circle is negative 4 cosine 2t. I've given you an equation. This describes the motion of my particle. I can ask you, what is omega and what is A? This is omega. So omega is going to be 2. And then if I have omega squared A, negative omega squared A is equal to 4. I already know what omega is, so now I got minus 4A is equal to 4. A is going to be 1, or negative 1. Sorry, it's going to be negative 1. So I can go in there and read it right off of my equation. And a couple of your homework problems literally are this easy. All you have to do is read the information right off of the equation. That's all you have to do. Now, here comes another fun part. Okay, another fun part is remember that we started out with omega is equal to 2 pi times the frequency is equal to the square root of k over m. All right, frequency is equal to 1 over the period. So I can have 2 pi. Your question over, Enid? Okay. 2 pi over the period is equal to the square root of k over m. I want period on top, So I'm going to flip everything over. So period divided by 2 pi is equal to the square root of m over k. So the period is going to equal 2 pi square root of m over k. So we can actually look at that as well. So if I tell you, and we sit there and we measure the time that it takes to go up and down here, and we find that the period is equal to 2 seconds, and we know that the mass on here is equal to 0.1 kilograms, I can find the spring constant for my spring. Or if I know the spring constant, I can find the mass that's sitting out there. So you can go and do those kinds of problems as well. But then it gets us to our pendulum. Okay, it gets us to our pendulum. So we can actually do things that look like this for pendulums. So basically for my pendulum, I've got my mass there. So we know that the force of gravity is pushing us down, mg. We have an angle that's going up here. And we know that the motion is going to carry our pendulum that looks like this, and we have the length of the pendulum, capital L. So the force that's going to cause us to go back down is going to equal and that's something that we kept seeing in physics 1. Circumference of my circle is 2 pi r. In this case, my radius is L, so there's 2 pi L. And this little distance traveled, provided that my angle is small. And that means less than 10%, or 10 degrees, usually. We can represent that S looks just like the edge of a triangle, and it's going to be my angle that looks like that. Or my angle can also be represented as the S divided by the L. So when I'm looking at my pendulum, that looks the way it goes. So now I can plug this in back into here, and I can say that F is equal to minus mg sine of my S and my L. Now it turns out for small angles, here's the representative for small angles. Turns out for small angles that the sine of the angle is pretty darn close to just the angle that you get yourself. So now I've got the force is equal to minus mgs over L. But I could approximate this system much like Hooke's law, and I can put that in here. So this is just the Hooke's law part. That's just the Hooke's law part. We can solve for K. K ends up being mg over L. And if I go back to my omega is equal to 2 pi times my frequency, which is equal to the square root of k over m. I substitute in for my k. I end up with mg divided by L divided by m. M's cancel. I get the square root of g over L. we can go back and look at our period part and do this in terms of period. Remember, I had t over 2 pi is equal to the square root of, it was m over k. Well, this ends up now being the square root of L over G. Or I can say that the period is equal to 2 pi times the square root of L over G. And that gives us the period of any pendulum, if I know the length of the pendulum. How's that? So if I know the length of the pendulum, and I can count the period, I can measure gravity. So you can take any piece of string, know the length, count the period, measure gravity. Provided that you don't have a really big angle. Because if I get the really big angle, I cannot use that approximation right there. But that's okay, because I get really severe dampening if I use really big angles. I get really severe dampening if I use really big angles. And if I want to solve for G, G ends up being G is equal to 4 pi squared L divided by the period squared. And I'm pretty sure you've got a homework problem that puts John Glenn on the moon and he takes out his little pendulum and he measures gravity on the moon or something that looks like that. And you're likely to see an exam question that says, okay, you've landed on planet X. Your pendulum is 1 meter long. You calculate the period to be 0.2 seconds. Find gravity. And I think I'm going to stop there. And I'll see you guys on Friday over in Enid, and you guys get to be through this part over here.